During this session, we're going to try and get to grips with how much energy is involved with nuclear reactions. Now, to do that, we're going to have to go back to some basics. So I'm going to introduce a term called the unified mass unit, which is the unit which we use to describe mass in these kind of situations. And then I'm going to state and apply Einstein's mass-energy equivalence relationship, which I'm quite sure you might have already come across as the idea of E equals mc squared. So let's introduce those ideas one at a time. First up, I'm going to think about the unified mass unit. Now, when we're talking about mass at an atomic level, the kilogram becomes a huge unit compared to the mass of one proton or neutron, or even more so an electron. So scientists decided that they'd create an equivalence unit just because it would help the science and calculations. And this became the unified mass unit. It's defined as 1/12 of the mass of an unbound carbon-12 nuclide. Okay, so 1U, unified mass unit, is equal to 1.66 times 10 to the minus 27 kilograms. And the idea is that this is to simplify things by getting a more manageable number. So that's the unified mass unit. As it happens, we have fixed values which we can look up for the mass of an electron, mass of a proton, mass of a neutron, and mass of one hydrogen atom. So these are all absolute. And now what we're going to do is we're going to try and think about or apply these numbers to some interesting situations. And that's where we're going to move on from there. So, Einstein and his big equation. Einstein came up with the idea that mass and energy were interrelated. And during nuclear reactions, mass is actually converted into energy. This happens in stars and nuclear reactors and nuclear fission bombs. And it all relates to the fact that energy and mass are, I guess, interchangeable depending on state. Okay, so the amount of energy produced by mass is changed into energy is given by this one formula. Energy equals mass times the speed of light squared, which is famously known as E equals mc squared. So this formula allows us to work out how much energy is trapped or held within a certain amount of mass. Okay, for an example here. Units. Energy in joules, mass in kilograms, speed of light in meters per second. The mass in kilograms is a big feature here. Okay, because remember I've just introduced the unified unit mass, and yet this requires typical kilogram. So there's always some conversion. You need to be wary of that. So a mass of 2 kilograms is completely converted into energy. As the speed of light we know is 3 times 10 to the 8 meters per second. How much energy is released? Try and do this calculation. Press pause. Now let me show you what answer you should have come up with. The formula we're using is E equals mc squared. 2 times 3 times 10 to the 8 squared, which gives me 1.8 times 10 to the 17 joules. As it happens, that's equivalent to burning 40,000 kilograms of coal. So 2 kilograms, if you could really convert that completely to energy, there's a lot of energy locked up in relatively small amounts of mass. So the fact that the human race has yet to fully find ways to effectively release that energy. Now, I've introduced a mass term, and I've also introduced the fact that mass is related to how much energy there is. There's a thing which you need to be honest about. There's a thing called the mass defect. And this is, I guess, a fortunate quirk. It was noticed that if I calculate the mass of a helium atom from the known unified mass values, so I've got 2 protons, 2 neutrons, and 2 electrons. If I look those values up and add them up, I get a value which is 4.032982 unified mass units. However, the actual value when measured was 4.002603 unified mass units. There was a difference here, and this wasn't understood. How comes the actual mass is different to that of the constituent parts? Well, what was identified was there was this thing called the mass defect, and there generally is a difference between the calculated value from adding up all of the constituent elements and the actual value. And this is explained using the ideas of Einstein. This mass defect, this difference in mass between the two situations, can actually be explained. It can be explained by the fact that this defect is actually the binding energy of the nucleus. This is the energy which is used to keep the nucleus in position. This mass difference also provides energy in nuclear reactions. Okay. So it's the releasing of this energy, which is locked up in binding nucleuses together, that we tap into in that situation. So we have returned to energy equals mass change times speed of light squared. Thinking about my example here, I've got for one unified mass defect, so I've got 0.03038 unified mass units. Now, if I multiply this by 1.66 times 10 to the minus 27, that tells me how many kilograms of mass I've got, and I multiply that by the speed of light squared, and it gives me a value of 4.538772 times 10 to the minus 12. Now you'll notice here, and this is kind of important, that this is one of those times where we try and maintain as much accuracy as we can until we come to the end of the calculation, and then we'll look at to what number of decimal places we can be able to present an answer. Although this answer is in joules, you might quite often be asked to give the answer in mega electron volts. It's kind of the standard unit of energy in this situation. So there's two ways which we can go about this. Method number one, converting joules into mega electron volts. It's a given value that one unified mass unit is equal to 931.5 mega electron volts per speed of light squared. So that means if I just multiply the mass defect by 931.5, it gives me the number of mega electron volts energy trapped. There is another way of doing that. I can think about how much energy I had in the first place, which is 4.538772 times 10 to the minus 12 joules, and divide that by the charge on an electron, and it gives me 1.6 times 10 to the minus 19, and that will tell me how many electron volts I've got. Both methods give me a final answer of 28.3 mega electron volts. So those are the types of calculations that you're going to be asked to look at in these types of questions.